What if space, time, and the forces of nature all emerge from a deeper underlying structure? Causal Fermion Systems is one of the most original attempts to rethink the foundations of physics. It's a novel approach to unifying gravity, quantum theory, and particle physics. And in this episode, I speak with its creator, German mathematical physicist Felix Finster, to explore what the framework is all about. In Felix's view, it's the matter particles, the fermions, that are truly fundamental. From their correlations, space-time, the force of nature, and everything else emerges. This is the Escape Sapiens podcast. If you appreciate these conversations and want them to continue, then please subscribe and share with like-minded people. And now, here's Felix Finster. I hope you enjoy.
Escape Sapiens.
You know, I've wanted to have you on the podcast now for some time because in terms of the physicists who I know personally, you're one of the most original, and you have a proposal for more or less how we should reformulate all of physics, which you've been working on for, 20 years now?
Well, more than that. Maybe I started in 1990, so it's around 35 years, right?
Right. Well, and the majority of that time, you've more or less been working on it alone. I mean, now you have more people.
Yeah, exactly. So most of the time I just worked it also on the side because it wasn't clear how to do it and how to proceed. So I just did it in my spare time most of the time. And then, I started more concretely, say around 1997 maybe. And then in the past few years, it became more my main dedication.
So that's what I want to ask you about, right? I want to ask you about the formalism, what it is, what is Causal Fermion Systems. But first of all, your origin story. I want to know how this began. So what was the original idea, that spark of inspiration, the thing that told you that maybe there was something deeper to physics than fields on curved manifolds, that there was some better way of doing things? Do you remember the initial spark?
Well, I think there was not one initial spot. It was more that, I was a physics student at the time in Heidelberg, and I liked physics very much. I was quite dedicated to that. And then I was in a quantum field theory lecture, which I did not like anymore. So I felt unhappy. Because up to a certain point, more specifically, including the Dirac equation, I liked physics very much. I liked the math, the formalism behind it, and I was really convinced that this is how you should describe physics. But then at some point in the quantum field theory lecture, I had the feeling I was not really I still understood what was going on, but I was no longer convinced by the way it was presented and also not by the content itself. And this is then when I felt unhappy. It was even like a bit of crisis, personal crisis also. And I was thinking about can't you do better than that? Of course, in a very naive way. And I think like most young people, students, maybe they have some ideas. But typically then students, from my point of view, they give up too early.
Right.
So I'm quite persistent, as a person. So, I kind of pursued this for quite some time. It was a bit like an obsession, you could even say. And this is then how things evolved. And at the beginning, it was quite a vague idea. Of course, I didn't really know how to do it. This is also what I said earlier. This is why I did it more in my spare time, more as a hobby, because it was quite vague. I had a certain idea behind it. Was based on this Dirac Sea picture. But this might already get too technical for the audience.
No, we'll get into this.
Okay, fine. Let's do this later.
But what I want to know, though, is because this is quite interesting, right? So for decades now, 3 decades, more or less, you've started on this route. And as far as I know from speaking to Claudio Paganini and various people who you work with, and initially there was some skepticism about what you were doing, and you had some pushback from big people and this sort of thing when you tried to speak about these ideas. And so what I want to know is sort of what kept you going, right? But what was there some moment when you realized, hey, I'm actually onto something here? Because now you have a formalism and you've got all the work behind it and you have quite a coherent picture now. But originally, when you're building that path, what kept you going, especially in the face of people being skeptical, let's say?
Good question. First of all, it's true that people were skeptical. in particular, the physicists were quite skeptical. I mean, at the time I studied physics and I also studied math at the same time. And my math professor was quite supportive because he knew that there's some interesting math going on. But the physicists were quite dismissive also because they didn't even take the time to have a closer look. So, I mean, I went to their office hours and told them, look, I mean, I typed something up. What do you think? Do you think this could be a possible topic for my diploma thesis or master thesis? And then they said, well, I'm quite busy right now. Maybe just leave it here. I'll get back to you. And then I didn't hear anything again. So I was quite frustrated also because this didn't... this was not my concept of how science and physics should be, right? I mean, I was thinking, well, these are physics professors. They should be interested in physics. So if someone comes with an idea, no matter how crazy it is, they should have a close look and be interested in it. And this is not the feeling I got. And then I was first quite frustrated. And then fortunately, like my math professor tried to, support me. And this is also then why I decided to change my studies from physics to math. So I decided to get a diploma in math. And also I felt more comfortable in the math community because my feeling was that they are more open, they are more tolerant, and they are also more interested.
As long as you can prove it, right?
Sure, of course. This is kind of the drawback, or this is kind of the basis, of course. If you are in math, you have to prove something. It all has to be rigorous. And you have to be willing to do that and also be able to do that. But I mean, I liked math. So, I mean, for me, it was the right path to go. And then, well, maybe at first I put this physics project on the side because I knew that there was I didn't see any future. And also people I talked with, for example, while I was a PhD student in Zurich, I also talked to some math physicists and physicists, and they were also maybe not dismissive, but they kind of told me you should better do something else. You will never make a career if you proceed with that. And then I decided, okay, fine, then maybe I should put this on the side. But I didn't really drop it. And it was clear to me that, my plan then was, well, in fact, I didn't really have a clear plan. Let's put it like that. I knew more what I didn't want to do, and then basically by excluding other options, then I ended to go to continue in math, and I was very lucky and happy to become a postdoc at Harvard with Xingtung Yao, and he was also a very good advisor. So he told me I should really. I also told him about these ideas, and he was he partly interested, but also he felt that it was not the right time yet, and also it's not maybe not. The mathematics behind it was not yet deep enough. And then he gave me advice to just do math, and this is then what I did, and I kind of tried to establish myself, which also worked out quite well, also due to a few lucky incidences, I should say. I mean, looking backward, it is really a bit surprising that with my kind of naive or
wild ideas.
Yeah, and also I was not really thinking, I didn't do any career planning in this sense. But nevertheless, in the end, things worked out nicely. And then when I came back to Germany, I was then in Leipzig at the Max Planck Institute, and my advisor there, Eberhard Seidler, he was really interested and supportive, and he said, well, you should proceed with that. And also you should write your habilitation on that. And then the idea, so my plan was simply to work it out step by step, writing math papers. So that simply because in mathematics it's easier to establish any new ideas, because as long as you prove something and some interesting math is going on, it is accepted or appreciated.
So you built up the blocks of the formalism piece by piece as a mathematician, and then when you got tenure, you put them all together.
Yes, and of course also gradually. The position I got here in Regensburg is like for PDEs or analysis. So I was hired here as a mathematician, and also I'm giving math lectures here. And also, as I said, I liked math, and a lot of my research also was in this kind of applied mathematics direction. And then gradually I moved more towards physics, also because the mathematical part was better worked out or better established.
But so let's go back then to your dissatisfaction, right? I was expecting you to tell me that there was some kernel of an idea or some beautiful image that you had, but really, so it started with the dissatisfaction. So then what was that? So what's wrong with describing physics by fields on curved spacetime, or what is missing from the standard approach that left you so dissatisfied and sort of kicked you off?
Well, there's several things. I mean, first of all, maybe it was simply bad luck. I mean, the lecturer I had in quantum field theory course didn't do a good job. In particular, what I didn't like his overall attitude towards physics and mathematics. I mean, first of all, mathematics was just a tool for him, which is in fact the attitude most physicists have. So he didn't take mathematical problems seriously. For example, I mean, in quantum field theory, typically you have divergent expressions, so some integrals are infinite, and then there are some computational tricks, computational rules in order to make these quantities well-defined, to get rid of these infinities. And of course, well, this is something one needs to do at some point, and I'm not criticizing this procedure by itself, but what I didn't like is the attitude behind it, which was basically,
calculate.
No, or even worse than that. It was more the attitude, well, if things are infinite, I don't care. I'm a physicist. I know if things go, I know why this happens because I have a physical intuition behind it, and I know what to do to get something sensible in the end.
But I must say, the difference between math and physics there is in physics, you can go away and do an experiment. So even if you're a little bit sloppy or you shoot from the hip a little bit, as long as your ideas are proven in experiment, it's fine, right? Even if you don't have a completely rigorous picture, which is...
Sure, I mean, I completely agree with that. This is also why I don't criticize quantum field theory, or let's say also the founding fathers of quantum field theory for proceeding the way they did. But I think that kind of... after some time has passed, it's important to clarify the concepts and to make everything also mathematically clear. Mm-hmm. And of course, you also need to be willing to do that, or you need to find it important to do that. And this is what I was missing. But as I said, maybe not in general, this was just a partly specific problem of the lecture I had back then. But as a young student, I mean, there's a lot of influence from the professors, from the lectures you are listening. So therefore, I mean, this particular maybe bad example or like bad luck I had. So this, of course, had an impact on how I proceeded in my career.
Okay, so divergent expressions, so things that blow up where you get infinities everywhere, that was one issue. But you mentioned the Dirac Sea. So the Dirac Sea is a key component of Causal Fermion Systems, your proposal, right? So what is the Dirac Sea, and what is it that physicists are missing about the Dirac Sea?
Okay, then let me try to explain in simple terms.
Yeah.
So the Dirac equation formulated by Dirac, I mean, this describes relativistic electrons. So this is the relativistic wave equation of quantum mechanics, of relativistic quantum mechanics. And already soon after it was formulated by Dirac, it was noticed that it has solutions of negative energy. And then people asked, well, what should a particle of negative energy be? And Dirac's solution to this problem was to postulate that in the vacuum, all these negative energy states are filled. Mm-hmm. So this means the naive picture, or the intuitive picture, is that the vacuum is not just empty space, but it's just a filled sea of quantum mechanical particles, each of which has negative energy. And then in view of this, the Pauli exclusion principle, which states that each quantum state can be occupied only by one particle. If you add additional particles into the system, they can only occupy states of positive energy. These are then the electrons. And what one can also do, one can also create holes in the sea. So I can take out a particle from the sea and bring it to a state of positive energy. Then this gives a state of positive energy, a particle, plus a hole in the sea, which is then an antiparticle. Mm-hmm. So this was the original idea by Dirac. And this was very successful in the sense that it led to the prediction of antimatter, which was also discovered soon after. So in some sense, this picture was highly successful. It led to immediate physical predictions. On the other hand, it has problems, at least if you look at it from a kind of naive point of view. Because if you think of in empty space, you have an infinite number of particles flying around here. They all carry negative energy. This means if you compute the energy density of this Dirac Sea, this is infinite and negative. And similarly, the charge density also is infinite. So therefore, this is kind of the reason why then physicists said, well, this was this naive picture by Dirac, but this has to be accommodated in the mathematical formalism in such a way that in the end, again, I'm simplifying a bit, so that in the end, like this Dirac Sea no longer appears in the mathematical formalism. One only works with particles and antiparticles.
So you scrub out all the fields that you're unhappy with, in some sense.
Yes, and of course, and this is also one way of avoiding these infinities, which one has naively or at the beginning. And what I didn't like about this procedure is that it seemed quite formal and ad hoc. I mean, basically, there is something you don't like, and then you simply throw it out and pretend it is not there. But I find this, or also found this, not satisfying, at least at the moment when there are other fields around. I mean, suppose you are in the vacuum. I mean, then the configuration is homogeneous and isotropic, and then the idea is that then the effects of all these particles cancel each other. Well, in simple terms, if one particle flies to the left, and there's another one which flies to the right, and then if you compute the total momentum, for example, you get zero. This, to me, makes sense. But it's problematic as soon as the configuration is no longer homogeneous and isotropic. So suppose you have a magnetic field. Then all these Dirac particles feel the magnetic force or the Lorentz force. And as a consequence, so in other words, if one particle is then deviated to the left and the other going the other way around, I mean, there's no cancellation anymore of the effects of all these C states. And this is why I thought, well, is there not kind of a net effect of all these C states? In other words, is this Dirac Sea not visible as soon as you are considering an interacting system? In the simplest case, you have a classical electromagnetic field around. Mm-hmm. So this was kind of the starting point.
I see. And just to jump ahead then, I mean, the Dirac Sea is a key part now of Causal Fermion Systems, right? It's one of the assumptions you take. You take the Dirac Sea seriously, and you build up from there, right? But so then, do you have a solution to this problem? I mean, shouldn't you be able to see the Dirac Sea if it's?
Yeah, exactly. So yes. So I mean, first of all, maybe the first idea is, well, if you have all these C states, suppose they are all real. So we are really surrounded by all these Dirac wave functions. And they all feel, for example, an electromagnetic field. Then don't they carry all the information on the electromagnetic field with them? So that was the idea, and this was already 35 years ago. The idea was, well, maybe the electromagnetic field is there only because all these wave functions feel it. Mm-hmm. Or in other words, maybe you don't need the electromagnetic field or electromagnetic potential as a basic object anymore, because it is just something you see as an effect on all these Dirac wave functions. So this was kind of the first starting point. Also, this is why it's called Causal Fermion Systems. So this is why these electrons or the C states, I mean, they are all fermionic particles, and the idea was that they should also carry the information on the bosonic fields, like electromagnetic field, gravitational field. So this is why how the name Causal Fermion System comes about.
I think so. I want to go further with this, but maybe it's a good idea to define what a fermion and a boson. So what's a fermion? What's a boson? Just in the conceptual picture.
Sure. I mean, well, in simple terms, all matter is made up of fermions. For example, electrons, nuclei, and so on. I mean, all the matter on Earth is made up of fermions. And then typically there are fermions which was considered as the elementary particles, so like the leptons, like electron, muon, tau, or the quarks, which make up the nuclei of the atoms. So all of those are fermions, and all of them are solutions of the Dirac equation. So the Dirac equation is really the basic equation describing all fermionic matter. And then there are additional, if you now want to describe the interactions of the fermions, so electromagnetic, strong, weak, gravitational, in the standard description, they are all mediated by, so this means that the photon, graviton, gluons, I mean, they are all bosonic fields.
I see. So if I restate what you're saying, you notice that you start with the Dirac equation and you have this Dirac Sea which appears just from the use of the Dirac equation, and you take this seriously. You say, this is one of my assumed things. I'm going to assume that this is the correct way to go. And from the Dirac Sea, which is just a sea of fermionic states, negative energy states, then space-time emerges, bosons emerge. Is that the idea? The rest is emergent.
Yeah, exactly. The rest is emergent. At the beginning, it was not space-time itself. At the beginning, it was just, say, the electromagnetic field. And maybe there's one thing which was also important early on. I mean, I already mentioned these naive problems of the Dirac Sea. So if you compute the energy density, it's infinite. The charge density of the Dirac Sea is infinite. So there must be a way to circumvent these problems. And my idea, again, very naive, as I said, I was a third-year physics student, was maybe the way the physical equations are formulated is not the right way to do it. Maybe, I mean, I agree that it doesn't make sense to write down the Maxwell equations because the current on the right side diverges. Maybe one has to write down equations of a different type. And this is then what eventually lead to this causal action principle, which is now the basis of Causal Fermion Systems. And the idea was, as I said, I mean, the central ingredient or central object were all these wave functions. And already very early on, I wanted to formulate physical equations directly with this family of wave functions.
So with any formalism, you have a set of assumptions, right? So even with the standard way of dealing with physics, so quantum field theory, let's say, you have a set of a priori assumptions that go in, and then from there, you can prove certain facts about the universe. So in terms of, I want to get an idea of what you put into Causal Fermion Systems and what you get out and how that stacks up against our standard description of nature. So let me ask the question like this. What is a Causal Fermion system? And what goes into it and what comes out of it? Just in broad strokes.
Sure. Maybe just first in general terms, I mean, I agree that you have to take a starting point for your theory, and which starting point you take is pretty much a matter of taste or a matter of choice at the beginning. Nobody really tells you a priori what the basic objects should be. There are different points of view, different theories, different ideas, and this is also, I think, how it should be. But I mean, now in my case, I mean, I have made a certain choice for myself. I said, well, I want to consider these wave functions as the fundamental objects. And then the question is, how, if you start from there, where do you get and how do you proceed? And of course, this is then how things evolved. Also, in the formulation now, it's not directly the wave functions which I work with, but with measures on linear operators on the Hilbert space. But all this came much later. I mean, coming back to your question, I mean, so I guess you wanted to know, like, in the setup we have now, what do we put in and what comes out?
Yeah.
So what we need to put in is what is the configuration of the fermions in the vacuum. And here we have to put in, first of all, that we are in a four-dimensional space-time, that we have electrons, so that we have the leptons, electron, muon, tau, that we have the quarks in 3 generations, and that there are the neutrinos which break the left-right symmetries or the chiral symmetry. So there are certain, this is kind of the input, and this is, let's say, this is of course a small subset of what is the input if you want to formulate the standard model of elementary particles. Mm-hmm. So I really put in less. But still, I need to put in something. In simple terms, I need to say what is the vacuum configuration.
I see.
Including these, and to me, the pictures, you have to say what are all these Dirac Seas.
For someone who has no idea of what a causal fermion system is, or someone who also doesn't have a background in physics, what is it? So when you say you have a causal fermion system, what are the objects? You have a measure, you have a set of operators on a Hilbert space. What I'd like to get is a conceptual picture of what those objects are, and then how those objects relate to the standard way of describing physics in terms of fields and metrics and this sort of thing. So what is a causal fermion system in precisely, and what's that mapping to regular physics? What does it look like? Okay, so good question. Of course, this is difficult to explain because it's quite mathematical and I can't start writing formulas here on the blackboard. So maybe the first important object is a measure. This is something which is well known in mathematics, and for physicists it's already a bit different because there's often confusion. People say, so it has nothing to do with the measurement process or a measurement. A measure here is just a mathematical object which allows you to perform integration in simple terms. Or if I try to do it in even simpler terms, it's something where a measure allows you to associate to a set its corresponding volume. So then if you take whatever, two sets, then their volume is just the sum of the volumes of the individual sets. So this is how to think of the measure here. And now in the case of causal Fermion systems, it's a measure on linear operators of a Hilbert space. Now, what does this mean? The Hilbert space, this is the basic object, say, in quantum theory, because the wave function, which describes, say, a particle in the simplest case, you think of a Schrödinger wave function. This wave function is a vector in a Hilbert space. So this means there's a scalar product, and you can this makes it possible to speak of probabilities and things like that. So this is like what a Hilbert space is. And now an operator on a Hilbert space is like something which acts on the Hilbert space, and you can think of this, at least in the setting of causal Fermion system, that it tells you how all the wave functions of the system look like at one space-time point. So you have one operator, and this tells you how do all the wave functions look like, and what are all the correlations of the wave functions. Mm-hmm. And by wave functions, you can think of, as we mentioned earlier, all these wave functions forming the Dirac Sea, for example. Mm-hmm. So one of these operators tells you about the configuration of the waves at a single space-time point. Mm-hmm. And now one considers a whole set of linear operators, and you can think of those. These are kind of all possible configuration of wave functions at space-time points. Mm-hmm. But not all of these space-time, or not all of these configurations are really realized in our physical system. So you have to select a few of these operators and say, well, these are the operators which make up our space-time. Mm-hmm. And this is done with the help of this measure. In simple terms, where those points where the measure is non-zero, these are the points which make up our physical space-time. Mm-hmm. So this is one purpose of the measure. And the second purpose is that you can also form volumes. In other words, if I take like a subset of space-time, I can associate it with a certain space-time volume. And this is important for the mathematical setup, because if you want to formulate this causal action principle, you have to integrate with respect to this measure. But I guess then it gets a bit too technical, right? Okay, so if I try to, so the way I think of what you're talking about, let's talk about finite dimensional things. So rather than infinite dimensional space-time, just some very large space. Sure. So the operators, those are just like big matrices.
Exactly.
Right? And those big matrices, just the numbers in the matrix tell you about the configuration and the correlation between all different fields, particles at a given point.
Exactly. So you can think of as the diagonal entries of this matrix are the kind of densities of the individual wave functions, and the off-diagonal entries tell you about correlations of different wave functions.
And so the size of the matrix then has to do with how many fields you have?
Or how many wave functions you build up the Dirac Sea.
I see. So the idea is let's say you had 10,000 wave functions, then you'd have 10,000 by 10,000 matrices,
exactly.
And you have lots of these matrices, and each matrix tells you about the correlations of these particles at a point in time.
Exactly.
And
at a point in space-time.
In space-time. And then the measure sort of ties everything together, and it's not that they're individual points, but it knits together the space-time and makes it so the points have some relation to one another.
Yes. So in fact, maybe I should say like this. Now, suppose we have now all this collection of operators. So each operator describes one space-time point. What you need also is get correlations between the different points, or say you want to have, for example, the causal relations. These points should not just be separate. There should be some connections between them. And this can be obtained in this setting simply by composing the operators. You take the operator describing one space-time point, so this big 10,000 times 10,000 matrix, then you multiply it with another 10,000 times 10,000 matrix describing another space-time point, and then you get another big matrix. And by looking at the properties of this matrix, then you can infer, are these two space-time points time-like separated or space-like separated? Are they close together or far apart? All these things are then encoded in these operators.
I see. And so the picture is, I could start with the normal way of describing space-time and fields in that space-time, and then I could go in the direction towards causal fermion systems. So I could start with the usual description of physics, and then from that I could build up these operators at each point, and I could build up a measure. And you're saying you can go the other way.
Exactly, one can go both ways. If you start from a classical space-time and you give me a family of, say, spinorial wave functions, they don't need to be solutions of the Dirac equation, just any family of wave functions. Then one can construct this so-called local correlation operator. So this means I evaluate all the wave functions at one space-time point and form inner products. This gives me then the matrix elements of this local correlation operator. And this is then the operator I take for the causal Fermion system. And I do this for each space-time, say for each point of Minkowski space. In this way, I get the causal Fermion system.
I see.
But you can also go the other way around. If you start from an abstract causal Fermion system, then you would say, okay, the support of the measure, so all the points where the measure is non-zero, this is what forms my space-time. These are the space-time points. And now these space-time points come with extra structure because each space-time point is this big 10,000 times 10,000 matrix.
Or more.
And the information contained in all these matrices, this is then what gives rise to families of wave functions in this abstract space-time, causal structure, fields, and so on. So you can really recover. So suppose you go back and forth afterwards. If you start in Minkowski space with a certain configuration of fields, and then you have a sufficiently large family of wave functions, you can go to the causal Fermion system and then start. If you take the resulting causal Fermion system and then construct a space-time, you get something which can be identified with the space-time you started from. This means up to identifications, you can really recover the whole classical space-time you started from the structures of the causal Fermion system. In other words, no information is lost.
I see. And I guess the point here is so the main point though is that you have this mapping back and forth between the usual physics and this abstract way of describing physics. And it sounds like you don't need every point in space-time. Like it sounds like the causal Fermion system could have some subset of the points in space-time, and that's enough. Right? In some sense, you could have a completely discrete space.
Yeah, exactly. So what are these procedure which I just explained. You start from a classical space-time, you construct a causal Fermion system, and you go back. This only gives you a very specific class of causal Fermion systems, namely those which correspond to classical spacetimes. But on this setup of causal Fermion systems, you can do much more general things. You can consider discrete spacetime, you can consider non-through spacetime, something within higher dimensional stuff. You could even have genuine quantum spacetimes. For example, if we also analyze this quantum field theory limit, and in this case, what you end up with is like a measure whose support is much larger than what you would expect. It's not just four-dimensional. All the additional internal degrees of freedom, so to speak, are also part of the measure describing the causal Fermion system. So the benefit I see that the causal Fermion system, the setup a priori is much more general. You can describe all kind of crazy spacetimes, if you like. And what is also important is that although you are in this very general setup, you can still formulate physical equations, which is not so obvious, because if you just consider a collection of spacetime points, you cannot formulate the standard usual equations anymore. So what should be a derivative? I mean, if you, for example, in simplest case, you want to take a derivative of something, then you have to take something like a difference quotient. You have to know where 2 points are close together. I look at the differences of certain quantities at 2 neighboring points, and then taking a certain limiting procedure, I get the derivative of a function. You can't do this anymore if you just have a collection of points without knowing which is close to what.
Which is what the measure.
Exactly, this is what this measure description does. So this is why one has to really come up with a different way of formulating equations.
So I sort of see the benefit then, right? Because in the standard case, when you're dealing with, say, just Minkowski, so just flat space-time, you can go in one direction and you can construct the causal Fermion system, right? But in the language of causal Fermion systems, you can be completely agnostic with respect to what the geometry is. Right? So in the regular framework, when I'm dealing with quantum field theory, the usual assumption is I can keep zooming in and zooming in and zooming in, looking at higher energies, and you still just have a background which is just regular geometry, right? And that's quite a large assumption. Right? What you're saying, what causal Fermion systems allows you to do is to be sort of agnostic about what the geometry is as you zoom in closer and closer and closer. I see. And it's in this sense that you might, if you're lucky and things go well, be able to resolve black hole singularities and do interesting things beyond the usual setting.
Exactly.
So one aspect of the construction that I don't fully understand is, when I read your book, one of the starting point is solutions of the Dirac equation, right? You have some Hilbert space of solutions, and generally speaking, when I think of solutions to the Dirac equation, I'm thinking classical solutions. And so what I want to understand is causal Fermion systems classical, quantum, or something else, right? Because it seems like the basic elements in your Hilbert space are solutions, which are classical, no? So how does quantum mechanics come in?
Well, to me, the whole approach is quantum, because the basic objects are quantum objects. And if you know, I mean, the input, the concrete input, if you want to formulate a model, is how does the vacuum look like? And the vacuum is then built up of solutions of the standard Dirac equation. And by vacuum, I mean no interaction takes place. I mean, if no interaction takes place, then this is like this is kind of the starting point, the non-interacting starting point. And this starting point is also well founded from the more abstract theory. I mean, because we can't work with it. We have to go beyond the Dirac equation. And this is done using this causal action principle, which I already mentioned. This is a very general, very nonlinear variational principle, which then also includes all the quantum effects and so on. And the connection to the Dirac equation is made simply by the fact that if you build up these Dirac Seas, then you get a minimizer of this causal action principle, or you get a solution of the corresponding equations. In this way, we then have a specific solution to the equation, of course, also a boring solution because nothing happens, there's no interaction taking place. But this is needed as a starting point for then analyzing the interaction.
You mean Minkowski space, right?
Exactly, just Minkowski space with these completely filled Dirac Seas describing the vacuum.
So just for non-physicists, so what you're saying here is you start with a causal fermion system, which is sort of the simplest, most boring type of causal fermion system you can come up with, and what you derive is flat space-time.
Exactly, and also just a classical space-time, no quantum spaces or anything like that.
So then space-time is really emergent in your picture. Is space-time, this is a dumb question, but is space-time real?
Yeah, no, yeah, I mean, maybe then I should say something else before. I mean, what the question you asked earlier on, what do you need to formulate a physical model? This is a way to, I mean, what one does there, I say I consider a concrete space-time as simple as possible, and then I want to analyze the interaction afterwards. And this is something which can be done quite computationally and in detail. And but maybe this is not what you mean. I mean, in order to answer the question, is space-time emergent? I think this is not the right perspective to answer this question. Instead, I would better also say, I mean, we have this causal action principle, which is defined in full generality in a quite abstract mathematical setting. And then one looks for minimizers of a certain functional. And the objects we are working with there, these are measures on operators on the Hilbert space. I mean, we don't need any technicalities here, but the point is that in order to start minimizing, you don't need to start with a space-time. So I can start minimizing things, and it's not clear whether this really is a sensible space-time or not, or what is the causal structure of the space-time. So nothing of that has to be pre-assumed. Mm-hmm. And then, but then this action principle is
Can I stop you just for a second? Because there will be a lot of listeners who don't know what a variational principle is, let alone an action and this sort of thing. So before we jump in more deeply into the causal action principle and the causal action and how you came up with it, because as far as I know, this is something that you just by brute force over many years sort of derived. But we can get into that story in a second. But for people who have no physics background, what is a variational principle? What does it have to do with dynamics and describing physics and describing the universe? And I'll remind you what the follow-up question is, and then what is the causal action principle specifically? So what's the variational principle?
Okay, maybe first of all, I mean, well, it goes back to the 18th century, so that physicists noticed that it seems a good idea to derive the physical equations by thinking that you minimize a certain quantity. For the simplest case, I mean, you minimize the energy of a system, and then once you have the kind of the system with the smallest possible energy, this is then typically also the system which is realized in nature. So this is kind of a stable system. And this also corresponds to kind of daily experience. So typically things settle down to the state of smallest energy. Well, and then, of course, minimizing energy typically just works if you are looking for statics or non-time dependent situations. But it turned out that this idea of minimizing something, which is then called the action, it's no longer the energy, it's another quantity. So you minimize something, and then this optimal configuration you get, this is the one which is realized in nature, which describes the physical, which satisfies the physical equations. Well, in this idea, I think, it goes back to 300 years. I think it boils from Voltaire, it boils down to we live in the best of all possible worlds. I think this is maybe the philosophical formulation of this idea. And it goes back mainly to, I think originally to Maupertuis and later Lagrange, Hamilton. So I mean, this whole classical mechanics can be formulated in this setting. And so this has been very successful and also has certain advantages that you understand the connection between symmetries and conservation laws like energy conservation, momentum conservation, and so on. And then this idea has then been continued or followed up in classical field theory, like Maxwell equations or the Einstein equations can also formulate it using an action, but in this case no longer minimizing it, but looking for critical points, so like kind of extremal points of this action. So this is then how the Maxwell and Einstein equations are formulated. And then in quantum theory, this can also be used partly, for example, in quantum mechanics, so there's this Ritz variational principle. But at latest in quantum field theory, this was no longer so successful.
Mm-hmm. Well, in the path integral, the action appears, right?
Yes, but you no longer minimize the action by itself. I mean, you consider an integral over all field configuration, and then again, like critical points or stationary points play then a specific role in this path integral formulation.
I suppose this is what I meant when I asked about the classical solutions of the Dirac equation, right? This makes me think of a very classical setup.
Yeah, okay, exactly. Also, in the Dirac equation can also be is also a variational form, so it can also be derived from an action principle.
But so action is somewhat abstract, right? And took people quite some time to work out the link between an action and dynamics in nature. So you came up with this causal variational principle, and you have a causal action, which is quite abstract, right? It's very different to the usual action that people play around with in let's say, regular physics or standard physics. And first of all, what is it? Where did it come from? And why do you need a different action in your setup?
Yeah, sure. I mean, maybe I should first again point out, I think the action itself, I think it's nothing you can really grasp or really put in connection to the physical objects. Already in classical mechanics, I mean, you can see energy and momentum. These are the objects I can really measure, which I understand what this is. But the action itself is a somewhat more abstract concept, and it is introduced just because looking at the corresponding, by minimizing it or looking at the extremal points, you recover the physical equations. And in the causal action principle, it's somehow the same thing. And as I already mentioned, I mean, I wanted to formulate different types of equations in order to avoid these divergences, and also because I wanted to formulate these equations directly with this family of wave functions. And if you try to do that, and if you want to do this in a sensible way, this means respecting gauge invariance and so on, then it turns out there's not too much you can do. So in other words, the setup you end up with is very restrictive in what you can do. And then you could say, well, maybe this is not so good. But in fact, I liked it because I thought, well, as long as maybe this is just what one needs for formulating physics. Maybe all the other structures come later, but are not fundamental. So I was kind of happy to have a kind of very restricted setup, so to speak. And working in this setup, as I said, there were not too many things one could do. So this means this led me to a kind of comparatively small class of actions. And the kind of mathematical framework in which all of this took place was also quite limited. And then starting from there, it took quite long to come up with a correct action principle. I mean, having like a certain family of actions is not good enough. You want to say, well, this is the one. Mm-hmm. And this is something which took quite long, and also it was a quite computational path. And the guiding principle was, well, first of all, I mean, we need to get back the classical standard equations at some point. So we need to get back the Dirac equation, Maxwell equations, Einstein equations. Mm-hmm. Which you get. Which I get, and also partly this is how the action principle is designed, or this is how I came up with this specific action principle. Mm-hmm.
So you start with some fairly abstract quantities, like measures and Hilbert spaces and so on, and families of operators on these Hilbert spaces. And you have this setup where you construct an action from these objects. Mm-hmm. And what can you So you can derive the standard model. What can you get? So let me say it. Yeah. First of all, do you get the standard model? Do you get all the physics that we currently know about? Okay.
So this all comes out if you start from the correct vacuum. Mm-hmm. So now coming back to the earlier discussion, I mean, like if you want to derive the standard model or you want to get the standard interactions of nature, then you have to say, well, the vacuum should be described by a certain configuration of Dirac Sea's elementary particles, and they are really put in what is known about our world, about the elementary particles. And then this configuration turns out to be a specific solution of the causal action principle. And this is also how the causal action principle is designed, I should say.
Okay, so by that you mean if you had chosen some other configuration, let's say, for example, you chose some different set of input data, you would then not minimize the causal action, or what's the status there?
This depends. I mean, and it gets quite tricky. I mean, suppose I modify the vacuum configuration a little bit. For example, instead of taking 3 colors, I only take 2 colors. Mm-hmm. I again get a minimizer of
and
the
colors are the generations of
the generations of not the generations. I mean the colors of SU3 quarks, the quark colors. Yeah. So suppose I took only 2 quark colors, I would again get a minimizer of the causal action principle. The vacuum would again be a solution of my equations, but then the dynamics would be different.
I see. So, but so you wouldn't be able to. That means you wouldn't be able to select a different gauge group then?
Yes, then one would get different interactions.
Okay, so you derive the standard model gauge group as a minimizer of causal action.
Yes, if I start from my specific vacuum, then starting from there, I can now consider what happens if I now allow for interactions. Mm-hmm. And then if I restrict attention to, say, interactions via classical fields, classical bosonic fields, then one finds that the effective gauge groups must be those of the standard model. The SU2 couples only to the left-handed fermions and all of that.
You get chirality as well.
Yes. So what I need to put in is that the neutrinos break the chiral symmetry. So there is something, I don't need to be very specific, which breaks the chiral symmetry of the vacuum. And then as a consequence, the interaction, the SU2 interaction, so the weak interaction, only couples to the left-handed component.
Okay. And from speaking with other people who work in the area, so Claudio Paganini, so he says that you also get, so you do get the number of generations of fermions.
Yeah, exactly. So exactly, that's exactly. I mean,
So can I so you
maybe coming back to what I said earlier. I mean, suppose you reduce the number of colors by 2, you again have a minimizer, but you get different kind of interactions. Suppose now you modify the vacuum in a different way, then different things can happen. For example, if you choose only 2 generations of elementary particles instead of 3, again you have a minimizer in the vacuum, but then if you look at the corresponding interactions, nothing is allowed. So in other words, you do not get any interactions, not at all. So in other words, you just have the vacuum and nothing else. And if you now change different things, for example, suppose you no longer take Dirac Seas, you take any other configurations of wave functions, then typically you won't have a solution of the equations anymore.
I see. So it's extraordinarily restrictive, and it happens to be the case that the standard model is viable.
Yes, I would say so. And also the equations, I should say, the causal action principle itself is completely determined. So there are no free parameters in there. So you need parameters to describe how the vacuum configuration looks like. And this is it. I mean, this is then also what determines whatever, say, coupling constants and so on.
Wait, so then you have less free parameters than the standard model as well? Or
at least from the outset. I mean, the equations do not involve any parameters, well, except, in fact, just one parameter. So this parameter kappa. Anyhow, I mean, so there's just one parameter in the causal action principle. And then you start minimizing.
Wait, so you then derive all the particle masses, all the coupling strength?
Not quite. I mean, of course, ideally we would like to do that. The problem is that we don't know how the vacuum configuration really looks like. I mean, so we do know that these are Dirac particles, and we have these certain mass parameters which come up. First of all, we have to put those mass parameters as empirical parameters in. And then, I mean, one important kind of feature is also that of this causal action, of this causal Fermion system approach, is that all the objects have to be smeared out on small scales. So the idea is that our concept of space-time, so Minkowski space or Lorentzian manifold, should not hold on all length scales, but if you go to tiny distances of the order of the Planck length, then space-time should or might have a different structure. And of course, we don't know in detail what this structure is or should be. And also in the causal Fermion system approach, one does not need to be very specific about that, but it's clear that there is a certain microstructure which then has to be modeled, and this again involves a number of free parameters.
I see. And so the idea is ultimately you would be able to find out what the correspondence is between the input configuration and what you would measure in terms of the parameters of the standard model. And you don't yet have that map, but what you do have is you're able to get the gauge group, you're able to get the number of fermions, the number of generations, and so on. And the representations of fermions, sorry.
Ideally, it should be possible to get more out of it, so that the goal would be also to determine whatever mass ratios, coupling constants, to get this out. And also I worked on this for some time, but for the moment, I mean, the problem is that there are too many unknowns. I mean, we don't really know what the microscopic structure of space-time is, and as a consequence, there's no predictive power in this sense. So I mean, I can't give you a reason for mass ratios. I can't compute mass ratios or anything like that.
So do you view this as a theory of everything? Is this a competitor to string theory or loop quantum gravity or something like this?
I think yes. I mean, from the outset, yes. I mean, the setup is such that it should describe all interactions in a unified way. And this is also what happens. I mean, so we have like one action principle. There's only one basic object. So this is this measure. And all the other objects are emergent. So space-time is emergent, fields, wave functions, particles. All of this comes out of the framework of the setup. And also the limiting cases make sense, and always with suitable inputs. So, I mean, if I say, okay, this is my vacuum, then I get the correct gauge groups of the standard model, the correct interactions. I do get the gravitational field, the Einstein equations in a limiting case. One gets also quantum fields in another limiting case, which we worked out more recently. So somehow it's clear that you have one theory, which is like consistently formulated, also with few objects. And in different limiting cases, you get what you want. So in this sense, I would say it's really a theory of everything. But of course, maybe first of all, many questions remain open. I mean, it's not that I'm claiming, so this is the theory which explains everything. Also, I don't like this notion theory of everything too much because there are somehow this pretends that this theory can really explain everything. And this is not, of course, this is not as it is, and also that's not what I claim. I'm just saying that there is a unified mathematical setup which is mathematically consistent. And at the moment, I can say that in different limiting cases, I get the different well-established theories. So in other words, all the theories are kind of combined in one unified setup. And therefore, it has the potential that one day it will really give a coherent picture, and also it will explain, for example, what happens if you go to energies where these different forces maybe are unified and things like that.
So do you think it's sensible to search for a theory of everything then? Or, I mean, people throw around this term, right?
Yeah, I think so, yes. And also I think it would be good if there were more competing theories around. I think the way the field should proceed is that many people come up with different ideas and different theories, and then of course some are more successful than others, and maybe one theory can explain one effect, the other another effect, and then simply as a kind of honest and fair competition, then hopefully this will at some point lead to a theory which is then better than all the previous theories. Mm-hmm. And I would be happy to enter this game.
This competition.
Exactly.
But so then what would quantum gravity look like in your setup, right? Is Causal Fermion Systems a quantum theory of gravity?
Yes, although I mean I don't like the word quantum gravity too much, because it is a bit, it's not so clear what you really mean by that. I mean, some people think of quantum gravity, well, you start from the Einstein equation, from classical gravity, and then you try to somehow quantize that. But then there are approaches which say, well, I start from something different, say whatever, I start from strings or whatever, and then at some point I get a quantum version of gravity back. And so therefore, depending on who you speak with, people have different concepts of what they mean by quantum gravity. So this is why I don't like this notion too much. I mean, therefore, maybe if I try to explain what this Causal Fermion system approach should give or already gives, I mean, this Causal Fermion system also comes with intrinsic geometric structures. Mm-hmm. So this means you get, first of all, you have space-time points, and they are causally related to each other. But there is also something like metric relations.
There's curvature.
There's curvature. There's curvature. There's a parallel transport. So therefore, all these geometric notions are there on a quite abstract and general level. Mm-hmm. So in other words, there's something what you could call is a quantum geometry. So there's a quantum geometry there. And the causal action principle also tells you how the geometry is connected to the matter. In other words, how does all this interact? How does matter change the curvature of space-time? So all of this is also described by the causal action principle. Mm-hmm. So and therefore, in this sense, now depends what you mean by quantum gravity. You could say there is a theory which includes geometry, gravity, and is formulated purely in terms of quantum objects. This is what I would understand as quantum gravity. Mm-hmm. Of course, now if you talk to physicists typically, and also this is like a valid point. I mean, you have to say in the end, if you do quantum gravity, now what are the quantum gravity effects? And this is something you should then measure at some point. Mm-hmm. And that is not so clear yet.
Mm-hmm. So then what are the testable predictions of Causal Fermion Systems? I also include their postdictions, right? But is there anything that's really that stands out and which distinguishes Causal Fermion Systems from, say, competitor theories, since we're putting it forward for competition?
Yeah, sure. Okay, I mean, first of all, I mean, to me, it's already interesting that one puts in fewer structures. Mm-hmm. So for example, if I see, okay, I get the SU3 strong gauge group together with its coupling, I get this for free, then to me, this is a source of satisfaction, or it tells me whatever, maybe I'm on the right track. But typically, this is nothing I can convince other people of, because they say, well, we know all this already. And moreover, the problem is that the whole derivation is quite long. Mm-hmm. So therefore, for someone who doesn't have the time to enter all the details, it's not so easy to appreciate or to understand what is really put in, what comes out. So then people maybe they think, well, maybe in the end he put in what he gets out. And so this is also why I don't want to insist on this point too much. I mean, to me, this is more like a matter of, say, taste or of mathematical whatever. Is it how convincing is the setup of the theory? Is it conceptually clear and convincing? I would say that causal fermions do have an advantage. But if someone doesn't agree with that, I won't argue with it.
But you should argue. You should.
No, sure. But then there are a few, of course, so in other words, what we need is really like more concrete predictions or results. Mm-hmm. And there are a few of them. I mean, one is that, for example, this what we mentioned before, that only 3 generations of particles are possible. This is again something which I wouldn't be able to convince many people that this is really like a real prediction, because they would say, well, we know already that there are 3 generations of particles. So this is then the real things. Well, first of all, I mean, there is right now, so we have like a mechanism of baryogenesis, which is really like tied to the structures of a causal Fermion system, and
so
which is also
through this is through cosmological evolution you generate particles.
Exactly. So the idea is that shortly after the Big Bang there was no matter yet, so we had like a more or less like empty universe, so to speak. But then, as a consequence of the time evolution and of inhomogeneities, which then triggered a certain evolution, this also led to the creation of matter without antimatter. Mm-hmm. So therefore this goes beyond the Dirac equation. I mean, as I mentioned at the very beginning, I mean, the Dirac equation allows for pair production. You can always create a particle and an antiparticle at the same time. But this is not what you need for baryogenesis. We have to explain why is there matter here but no antimatter. Mm-hmm. At least much more matter than antimatter.
Mm-hmm. So you have a clear mechanism in causal Fermion systems.
Yes, and this is something we want to explore further and see, well, how, also more quantitatively. I mean, is this really...
does it match up with observation?
Exactly, does it match up with observation?
Is there something that would really kill the theory? So is there a result which would cause you to abandon the theory at this point? So, is there something that you predict which, if someone goes along and they do an experiment, then rules out the formalism?
Well, of course, I mean, first of all, I'm in favor of this competition, and also I'm in favor that physical theories are ruled out. Even, of course, I wouldn't be happy if causal Fermion system would be ruled out. I mean, I would clearly accept this, and the goal is also to make prediction which can potentially be ruled out, right? I mean, so and
which is what you mean when you say make the baryogenesis
exactly,
framework
when you have it quantitative, and in case, for example, the baryogenesis rate is far too big, then we have a problem, and then we have to try to explain this problem. And right now, I don't see really like a killer experiment in this sense. I don't quite see. I just see that some things do not come up in the causal Fermion system approach, which do come up in other theories. For example, I don't see a way that supersymmetry is built in. So I mean, also my concept is really that fermions and bosons are
separate,
different, fundamentally different objects. And this is really different from the supersymmetry idea, where you have symmetries, like fermions can be converted into bosons and vice versa. So therefore, if really like supersymmetry is discovered, then at least I would have to rethink the whole setup here.
I suppose that's, yeah. So that would be something that would, to a large extent, kill the formalism, right? And we haven't discovered supersymmetry, not at the Large Hadron Collider or any other collider.
Not yet. I mean, let's see.
Okay, so let's imagine that causal Fermion systems is really the correct way to formulate physics. What would be the biggest conceptual implication? And so what would that tell us about reality that we don't currently understand? Right. So currently I have this picture of how to build the universe using fields on space-time, but what's the conceptual picture that develops if this is really correct?
Okay, so the way I see it, I mean, this means so there is a certain minimization process happening. So in other words, something is optimized. We are trying to get into the best possible world, whatever this means. Something like this is there. And as a consequence, all the objects we observe come about. So which is then space-time and wave functions and fields and all of that. So they just come up as a consequence of this, whatever, minimization, optimization process. And to me also, it has certain, like also, if you think of, say, foundations of quantum theory, it has some impact. Also because the basic object then really just is this measure in mathematical terms, or this family of wave functions. So the wave functions is really what kind of carries all the space-time structures. And then if you ask then why, what about the particle in quantum mechanics? I mean, if you think of this double slit experiment, I mean, you see like this, there's a point on the screen, so like a point-like particle hit the screen. How can you describe that? And then my answer would be this comes about as a consequence of the interaction. And the interaction as described by the causal action principle. And this interaction is really quite different from the usual formulations. Mm-hmm. And then, of course, it gets a bit difficult to understand. Well, the difficulty is really to understand what does this causal action principle really do.
See, this is something that I should point out is very different to the way that regular physics is done. Right? So usually you parameterize a system, by which I mean you say I have such and such a particle, or I have this set of objects, and then I have an action which I minimize, and by minimizing that action, I work out the equations of motion that tell me how the objects move. So in your setup, if I understand you correctly, things are a little bit different because you have an action. Again, you have some quantity that you minimize, but through minimizing that quantity, you don't just get dynamics, but you also, correct me if I'm wrong, get the types of particles there are, the parameters in the system. So you get somewhat more through the variational principle.
Yes, exactly. And also the variation principle should be thought of more, you vary the space-time as a whole. So this is nothing which happens at a specific time or something like that. So therefore it's not...
It's a global...
It's literally, you have to think of space-time or our universe as a global object, which is then minimized, and you try to optimize the configuration of the whole universe.
Mm-hmm. It's like a wave function for the universe or something like this.
Yeah, not really wave function, it's different object, but of course you can think of it as it's like a global object, so to speak, which is then optimized. And in fact, this is not so different from GR. I mean, if you think of this, there's this Einstein-Hilbert functional, you look for critical points of that, and also there you vary the metric in all of space-time at the same time, or like, of course, there's no time anymore. I mean, you vary the space-time in all, the metric in all of space-time, and then you get a certain set of equations. Mm-hmm. And it's similar for the causal action principle, you get this corresponding Euler-Lagrange equations. Now, if you ask about the dynamics, then it's kind of a different question, because then typically you know this system at present, and you want to know how does it evolve in time. And if you want to answer this question, then you no longer look at this global variational principle. Instead, you ask the question, suppose now I have my Euler-Lagrange equations, or similar with the Einstein equations also. I mean, suppose now I have the equations which describe this minimization property. Mm-hmm. And now the question is, can I solve these equations given suitable initial data? Mm-hmm. And this is also something which has a quite nice setup in this causal Fermion system approach. And it's pretty much as in standard physics, except that everything is kind of smeared out on small scales. So instead of imposing the initial data at a fixed time, you have to impose the initial data in a kind of time strip, so to speak.
It's like an uncertainty principle of some sort. in some sense?
A little bit.
Does this mean, so there's this natural smearing that appears in the formalism. Does that mean you can resolve singularities in, say, the black hole or at the beginning of the universe? Or is that outside of what you currently...
No, this is also something, this would be part of it. So the idea is that if you go to very small distances, then the space-time structure is different. It could be discrete. It doesn't necessarily need to be. And in this way, also singularities, like in the center of a black hole, for example, or at the Big Bang, could be avoided.
But you don't yet have a picture of what that would look like.
No, I mean, exactly. So, I mean, I just wanted to say that. I mean, right now, if you now ask how does the black hole singularity really look like if you resolve it in this way, I can't answer this question.
So by that you mean that the mathematics itself is robust enough to describe a variety of different resolutions of a singularity, or what do you mean exactly?
Well, let's say first of all, the mathematical setup is well defined, even if you have such singularities. So the mathematical equations make perfect sense. But the difficulty is to find the solutions. I mean, if you ask me what are the solutions of these equations, how does the solution look like near the space-time singularity, then I don't have an answer right now.
But you do have an equation to solve.
Yeah, exactly. The equation, and it's clear
and
that
that's something, right?
Sure. And also this equation remains, it's clear that there will be solutions even if there's a singularity.
Okay.
So in other words, the solutions do not blow up, or you don't get infinities so the equations are still well defined.
Mm-hmm. I see. So then, in terms of the cosmology, this might provide a way of resolving the Big Bang and determining what it is or was. It's not something you've looked at, or?
Yeah, sure. I mean, I thought about this, but it's not so clear. Well, I don't have an answer right now. Also because I think that these notions of space so the conventional notions of space and time might no longer be valid. I mean, typically you say, this is what I mentioned with this time strip and Cauchy and the time evolution problem. If you say you take Minkowski space to describe the present universe, then we know that if you give me initial data, then there is a unique solution to the Cauchy problem. In other words, there is a unique time evolution. Mm-hmm. If you now go to this situation near the Big Bang singularity, this might no longer be the case. So in other words, you can no longer speak of there is no unique, you can't expect a unique time evolution anymore. Maybe it's no longer possible to speak of space and time at all. Mm-hmm. What you still have is space-time points which are kind of in relation to each other, but these relations could be quite different from what we are used to.
Is this what you mean? So at the beginning of the conversation, you said that in certain limits you can derive known physics. So you can derive Minkowski space or whatever the physics is that you're looking at in particular limits. By that, do you mean... So I'm starting to understand, I think, what you mean by that, which tell me if I'm wrong here. So you have an abstract mathematical description, and in certain limits, you can show that it aligns, there's a one-to-one correspondence in certain limits with known physics. And then there might be some really extreme physical circumstances, like the center of a black hole or the Big Bang singularity or something like that, where our regular description of physics, our regular notion of space-time breaks down, but this dual description in terms of causal fermion systems continues to make sense.
Exactly.
And you can write down the equations, you can analyze potentially the center of a black hole, but you no longer have this mapping back into the usual description because the usual description breaks down.
Exactly.
I see.
Exactly. Also because, whenever you want to really do physics, you want to describe the standard model or you want to describe curved space-time, the underlying assumption is always that on small scales it looks similar to Minkowski space.
That's a pretty big assumption.
This is a pretty big assumption. And then we thought, well, then if we go down to the Planck scale, there might be something different, but I don't really need to be specific because it is not relevant for what I observe now.
Mm-hmm.
But this could be drastically different if you are near singularity, because then this small-scale structure of space-time really comes into play and plays an important role. Mm-hmm. And then there's not too much known. I should say, one can analyze this mathematically quite well. If you start from this kind of abstract setting, you can still show there are minimizers, you can analyze the corresponding Euler-Lagrange equation, you can analyze which structures are there, how are they related, and so on. So there's a lot known on a quite abstract level. Mm-hmm. But then there's kind of a gap, right? It's not so clear how to connect this, say, to the real world, say, near a black hole, near the center of a black hole.
I see.
So yes, and the basic difficulty I see that we don't know how a general solution or general minimizer of the causal action principle looks like. Mm-hmm. Mathematically, you can prove there are minimizers and you can analyze their properties. But if you ask me how does a generic minimizer look like, I don't know.
I see. So you have this formalism, which it's very abstract. It's constructed in terms of measures and operators on Hilbert space and so on. And you can find regimes where it seems to reproduce what's known, but not only that, it reproduces what's known using fewer parameters, if I understand correctly. And the formalism continues to make sense when you push beyond where our current formulas or our current formalism makes sense. And so the hope is that when you push beyond what we currently describe in terms of quantum field theory and GR, let's say, the hope is that really does map onto reality. And you'd need to test it, right? You'd need to...
Sure, exactly. So, this would be the hope, or this would also be the program for the next years, I would say. Because as far as I see it, so the kind of the mathematical foundations are pretty much worked out. I'm happy with the whole mathematical setup, and also from the abstract point of view, there's a lot done already. There's this new book which just came out, or which will come out in print in October, where also there are chapters describing the different mathematical tools. So there's a lot of mathematical tools around which you can use to analyze the whole setup. And so therefore there's a lot done already. And what would be the next step is really try to get concrete predictions. So get into physics. Also, this includes, of course, making kind of longer computations, getting your hands dirty, as people say.
PhD students.
Well, also myself. I think these are not problems I could just give to a PhD student. I think I have to get my hands dirty myself as well.
Postdocs. Okay, at the beginning of the conversation, we talked about how initially people were relatively skeptical, let's say. You were a young student, third-year physics student, coming up with bold new ideas about how everyone should redescribe physics, or at least you were pointing out problems that you saw in the way that people were describing, say, the Dirac Sea and other areas of physics. Has that changed? Are people starting to come around to the way that you view things? Are people more accepting or less dismissive, at least?
Yes, so I think I do notice a change, of course, but it's goes slow and gradually it changes. And also because I think that the mathematicians were not dismissive right from the beginning. So this is also why I decided to kind of establish in math first, and but in the meantime also more and more physicists are beginning to take this approach seriously. Mm-hmm. And of course, it's difficult to say the physicists, because of course there are many sub-communities and so on. Of course, the people I talk most to are also like mathematical physicists or people working in mathematical quantum field theory or gravity. So these are the people I typically interact with, and I would like also to interact with, for example, experimentalists, and I talk to them, and I also got positive, this was also a very positive experience, that they also seem to be open-minded. The difficulty is then to, first of all, to communicate, so because of different languages, and also to come up with something which is so concrete so that physicists can really take it as a prediction and test it. Mm-hmm. And this is not so easy. Mm-hmm. And in particular it's not so easy also because the models which are around are typically quite complicated. They involve many different parameters, and simply because people have been working on them for many years, there's a lot of expertise which has been built up. And if you are not so familiar with all of that, then it takes time to, first of all, to communicate in a sensible way, and also to understand their problems better and try to find some common grounds here. But my feeling is that, I mean, for the more experimental people, I mean, they are very open-minded because they are not dogmatic. I mean, they don't stick to a specific theory. They just say, well, no matter how you make your prediction, just tell me what you want me to measure, which I also find a quite good attitude. This is somehow how it should be.
It's really the people in the middle, the physicists that aren't experimentalists, that are the problem.
Yes. Well, yeah, I mean, but to me, this is also partly a problem of physics itself. I mean, there are big communities in physics which are kind of a bit detached from real experiments. Mm-hmm. And this is how it has developed, also maybe partly because there was not so much experimental input anymore. Mm-hmm. And then the field kind of developed more on its own than driven by different schools, different people who promoted several ideas, and then the young people followed them.
But then how did you... So you worked on Causal Fermion Systems now for 30 years, something like this. And initially you just had an idea, right? Okay, you've built up this large canon now. There's a lot of consistency built into the construction. You've gone through and done checks and to make sure this really does align with the physics we see in experiment. How did you know not to get? Why did you know that this was sensible to start with? Right? I'm talking about if you go back 20 years. How did you know it was sensible then? Did you have the causal action principle 20 years ago?
Well, I had it since 2002. Mm-hmm. So a bit more than 20 years ago. And well, of course, the question is already early on, somehow it was more emotional. I felt, so this is how to do it. Although I didn't really know what I wanted to do, I felt this is it. Mm-hmm. And this is then also why I proceeded with that.
But so then what was the guiding principle, I suppose is what I'm trying to ask. It sounds like mathematical internal consistency is one of the key guiding principles, but you're trying to build reality, right? So what were the guardrails, I guess is what I'm asking.
Well, to me it was just the question, like the question is, what are the basic objects you want to work with? And somehow I felt that this is what should be the basic objects. Mm-hmm. And then starting from there, as I already mentioned a little bit, I mean, it was a quite restrictive framework. There was not too much one could do. And this kind of already led me to the path, which then eventually led to the causal action principle. Mm-hmm. And it was more, first of all, I mean, of course, being in this setup, I already built in a couple of physical principles. Mm-hmm. So kind of I think early on, I mean, of course, I knew a few principles or whatever, like equivalence principle or local gauge principle, Pauli exclusion principle. So I mean, and I liked those principles, and then I tried to kind of combine all these principles in a nice and small or like a tight mathematical setup. Mm-hmm. And maybe I should say, I also think pretty much in mathematical terms. I also notice this also when I talk to other people that to me, the mathematical objects, they speak for themselves somehow. So this means then when I try, of course I had these physical principles are typically not formulated in mathematical terms.
Mm-hmm.
But I wanted to kind of combine them in something simple.
Mm-hmm.
And then I found it convincing.
Mm-hmm. I suppose if you're doing any sort of measurement, a measurement is an interaction between particles, right? So at the fundamental level, what you have is particles. That's what we have in reality. If you go to the Large Hadron Collider and you look at experiments, you have colliding particles. You're never directly measuring space-time, right? It's the things that are sort of in space-time in some sense. And so it kind of does make sense to begin by turning the formalism on its head, right? And starting with the Dirac Sea or starting with the fields. And then seeing if you can back out other aspects of reality that we would usually start as the starting points, right? So in that sense, I can kind of follow your view.
Yes. So maybe I should also have mentioned. It sounded a bit as if the whole path was more mathematically driven, so to speak. But I think it's more like really. The way I see it. I also find it quite surprising that physics can really be formulated in terms of mathematics. So mathematics really seems the right language for describing nature, for whatever reason. I still find this quite amazing that it is like that. And this is what I tried to do. In other words, I wanted to try to build in the principle, formulate the principles in a mathematical language. And then, of course, there was a long path also guided by where do you want to get. In the end, you want the Maxwell equation, you want the Einstein equations, and in order to get there, you have to do certain things.
Mm-hmm.
But the whole kind of the general mathematical framework in which all this took place was already determined back then.
Mm-hmm. As a pop science question then, is mathematics invented or discovered? It's more of a personality question.
Well, I think that some basic mathematical objects are really there in nature. So they are realized in nature, whatever this means. But I wouldn't say that all of math is, I think that most mathematical objects are still man-made. People come up with definitions and also many definitions, in math you can do many things. You can study all kind of crazy structures in mathematical terms. But of course, I wouldn't say that all of this is really part of nature, right?
If you had a magic wand and you wave the magic wand and you can answer any question about causal Fermion systems, what's the one question you wish you had an answer to?
Of course, I would like to know if it really describes nature or not. So, I would like to know, say, in 1,000 years from now, what do people know about our space-time, and does this really make a fit?
Well, Felix Finster, thanks for coming on the podcast.
Okay, thanks a lot for the interview. Thanks a lot, Shane.